Okay, so find the interval of convergence and the radius of convergence. I'm about to say f of x. Of the series, the sum from n equals 0 to infinity of 3 times x minus 2 to the nth power. Okay. So we're just going to use the ratio test again to find out exactly where it converges, or where it converges absolutely. So you have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So this gives us the limit as n approaches infinity of the absolute value of 3 times x minus 2 to the n plus 1 over 3 times x minus 2 to the nth power. Okay, which equals the limit as n approaches infinity. We can go ahead and just separate your numerator. So you have 3 times x minus 2 times x minus 2 to the nth power over 3 times x minus 2 to the nth. Okay. And this is where stuff just starts canceling out. So your 3's cancel out. Your x minus 2 to the nth power cancels out. So that leaves you with the limit as n approaches infinity of the absolute value of x minus 2. Which, since there are no n values to increase, is just the absolute value of x minus 2. Okay. Now, since we're using the ratio test, the only way this can converge is if that limit is less than 1. Okay, so by the ratio test, the series converges when L is less than 1, which means that the absolute value of x minus 2 has to be less than 1. Okay. So we know the absolute value of x is less than r, is negative r is less than x, and that's less than r. The absolute value of x minus 2 is less than 1. Means you have negative 1 is less than x minus 2 is less than 1. Okay. So if we add 2 to each section, plus 2, plus 2, plus 2, I'll lower that just a bit. Okay. You have 1 is less than x is less than 3. Okay. So if we kind of draw out a number line to help us visualize it, and I'll put that x here, that's between 3 and 1. Okay, so if we're starting here, our radius is just the distance from the center to either endpoint. Okay, so we know the distance from 2, in this case 2, 2 to 3, and 2 to 1 is just 1. So our radius of convergence is actually equal to 1. Now our interval of convergence, we found that first, and that's between 1 and 3. Yes?
How do we know that it's exactly in the center of those two?
Oh, because it's centered at, it's a power series centered at 2.
I forgot about that.
Oh, no problem. So your interval of convergence is just from 1 to 3. All right. So any questions on that one? All right, I'll leave that up for a few seconds.
Is there a reason we wouldn't know the center, or will it always give us the radius? Like otherwise, would we have to like find the average between the interval points?
For usually, if you just subtract the 3 minus 1 divided by 2, well, not 3 minus 1 divided by 2, it's it.
3 plus 1.
3 plus 1 divided by 2, thank you. Yep, you find that, you can usually find your center point and just figure it out
That's
from
what
there.
I'm saying is like,
Unless it's really complicated, which I don't see any of the problems being that complicated, you can usually kind of figure it out.
sort of see it.
Yeah. Yeah, usually it kind of jumps out at you. All right, so let's say if we have, for example, if we want to find the radius of convergence and interval of convergence of the series, the sum from n equals 0 to infinity of -1 to the nth power times x to the 2n plus 1 over 2n plus 1 factorial. Now for this one, since you're using the absolute value, you can leave the -1 to the nth power out of it because it's always going to be positive. Since we are using the ratio test, uh-oh. -1 to the nth can be left out of our a sub n since we are using the absolute value. Plus, if you didn't take it out, it would cancel out anyway. At least the nth would cancel out. Okay, so if you have, let's say if we let our a sub n equals x to the 2n plus 1 over 2n plus 1 factorial. Close that up. Okay, so our limit as n approaches infinity, the absolute value of a sub n plus 1 over a sub n, that's going to be equal to the limit as n approaches infinity. Our a sub n plus 1 is going to be x to the 2 times n plus 1 plus 1 over 2 times n plus 1 factorial, divided by your a sub n, which is x to the 2n plus 1 over 2n plus 1 factorial. I just wrote it like that because it's just a lot less confusing. Okay, that's equal to the limit as n approaches infinity. If we distribute that 2, we get 2n plus 2 plus 1, which is x to the 2n plus 3. That's the absolute value of x to the 2n plus 3 over 2n plus 3 factorial. And we can go ahead and change that times, and we flip the second one. Say 2n plus 1 factorial, clean that up a little, over x to the 2n plus 1. Yep. Close that off. Okay. So now we want to be able to cancel out our x to the 2n plus 1 and our 2n plus 1 factorial. So we manipulate it a little bit. So as n approaches infinity, this would be x. You can rewrite it as x to the 2n plus 1 times x squared. Over, give that a little more room, 2n plus 3 factorial, you can make that 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So it just keeps going down further and further. Times 2n plus 1 factorial over x to the 2n plus 1. Okay, so here we have our x to the 2n plus 1 cancels out. Our 2n plus 1 factorial cancels out. So we have the limit as n approaches infinity of the absolute value of x squared over 2n plus 3 times 2n plus 2. Okay, so we can get our absolute value of x squared and just bring that right out to the front, since we're only going to be changing the n values. So you have the absolute value of x squared times the limit of 1 as n approaches infinity of 1 over 2n plus 3 times 2n plus 2. Okay. So we know we have a constant in the numerator, and our denominator is getting bigger and bigger and bigger. This is just going to approach 0. So here we have the absolute value of x squared times 0. Okay. Now the thing is, we know for it to be convergent, the limit has to be less than 1. But no matter what you plug in for x, it's always going to be 0, which means it's always going to be less than 1. So if it's always less than 1, then the x value doesn't really matter. So that means that any x value could be plugged in and it would still be convergent. Okay, so for any value of x, the limit is 0, which is less than 1. So by the ratio test, the series converges for every x. Okay, so that means your radius of convergence is going to be equal to infinity. And your interval of convergence is going to be from negative infinity to infinity. Yes?
When you factored the 2n plus 3 factorial,
Mm-hmm.
How come only like the constant went down and not like the 2n? Like, how come that doesn't change, but the plus 3 plus 2 plus 1 went down? You know what I'm saying?
I see what you're saying. I'm trying to think of the best way to explain that one. So just the constant, so let's say if you have, let me leave that up there for a second.
That's what a factorial is.
Yes.
essentially.
Yep. So if you have, let's say, 2n plus 1, so let's say if your n was 12. So 2 times 12 plus 1, so that would be 25. So 2 times 12 plus 1 factorial. So that would just equal, that's 25, so that would be 25 times 24 times 23 times 22, and it keeps on going all the way down to 1. So if you have this, that's just going to be 2 times 12 plus 1 times, well, I should have used plus 3, but
We just make them
yeah,
lower.
2 times 12, then that would, which is 24, then 2 times 12 minus 1, and then it just keeps going down from there.
Okay.
Just keep subtracting.
Yep,
one
exactly.
every time, basically.
Gotcha.
Yep, all the way until it gets
Or
to,
in this, or in our
Yeah.
case, it just was lowering that 3 to a 2 to a 1, because it's really 3 minus 1, 3 minus 2, 3 minus
Yeah.
3.
that's it.
Okay, thank you.
No problem. Yeah.
And why do we stop at 0?
Why do we stop
Where
where?
does it stop when?
We didn't stop, we just stopped at that point to write the factorial, because we
Oh,
only
yeah.
go to 2n minus.
Yep, this
1.
only it goes all the way down to 1.
Stops at 1.
Yep.
Yeah.
Because if you go down to 0, it just wipes everything out.
Right, okay.
Yes.
Can you bring back the other?
Oh, sure. Sorry about that.
And when we bring out the x squared, does
Mhm.
that need to stay in the absolute value for any reason?
It does only because when it's in here, it's that. Well, when it's x squared, it doesn't have to because it's
Right.
always going to be positive. But just out of habit, I always kept it in the absolute value.
Okay.
But yeah, when it's x squared, it's you could just leave it as x squared. Some things I do just because I've had flashbacks of losing points as a student, so I always do the same thing over and over. So even though it's not necessary, I still do it. So. Sometimes you learn more from the ones you get wrong than the ones you get right.
Most of the points I lose are from like skipping steps in my head.
Yep.
I'm like, oh yeah, like 3 steps from now it's gonna be this, so I'm just gonna go to this.
Yep, you automatically
And
know.
in those steps, I forgot an absolute value, or wait,
Yeah.
oh wait, no, it's to this power, not to that power.
So you assume, oh, I've seen this a million times. I know what's going to happen.
Right.
It doesn't happen that way. So. Been there. Oh, you want still writing? All right. And move this out of the way. Okay, so here, we're going to now look at representations of functions as power series. Uh-oh. And clean that S up a little bit. Okay, so we're going to go back now to our old geometric series. Where you have the sum from n equals 0 to infinity of a to the r sub n. That infinity looks a little iffy. Which is the exact same as the sum from n equals 1 to infinity of a to the rn minus 1. So any one of those you could use and you'd be just fine. Okay, but just for the sake of convenience, I'm using that one. So the sum from n equals 0 to infinity of a to the r sub n, remember the sum of that is equal to a over 1 minus r. And that's for the absolute value of r is less than 1. Okay. So let's say if we let a equal 1 and r equal x. And it's centered at 0. Okay. So if a is equal to 1 is r is equal to x, that leaves us with the sum from n equals 0 to infinity of 1 times x to the nth power, or just x to the nth power, is equal to 1 over 1 minus x. And that also means that the sum from n equals 0 to infinity of x to the nth power, if you plug in 0, you have 1. If you plug in 1, you have x. Plug in 2, you have x squared, x to the third, etc., and so on. Okay. So if both of these are true, that means that these two would have to be equal. Okay, so that means that 1 over 1 minus x would have to equal 1 plus x squared plus x to the third, etc., and so on, when the absolute value of x is less than 1. Because remember, that was stipulation up there. Okay, so this is what we're going to use this idea to obtain our power series. Right. P1 still writing. All right. Okay, so let's say, for example, let's say obtain the power series for f of x equals x squared over 1 plus x squared. Bring that down a little bit. Okay, so to do that, again, just a quick reminder that the sum from n equals 0 to infinity of a times r to the nth power is going to be a when n is equal to 0 plus a times r squared, and it all adds up to equal a over 1 minus r. So that's 4, absolute value of r is less than 1. Okay, so if we have our f of x equal x squared over 1 plus x squared, and we can rewrite that if we divide everything by x squared. So we have x squared over x squared divided by 1 over x squared plus x squared over x squared. Which, if we go ahead and just switch those around, we have 1 over 1 plus 1 over x squared. Okay, but the thing is, we want to match that. So we can make that 1 over 1 minus negative 1 over x squared. Okay. So in this case, we know our a is equal to 1, and our r is equal to negative 1 over x squared. Okay, so if we know that from n equals 0 to infinity, a to the r sub n, that's going to become the sum from n equals 0 to infinity. You don't have to put the 1 there, but I'll put it just as kind of a placeholder. 1 times negative 1 over x squared to the nth power. Okay, which is equal to, I'll put it underneath so it won't cram up things too much up there. That 1, you can, like I say, you can kind of let that disappear. So the sum from n equals 0 to infinity. There we go. There we go. If you want, you can look at that as negative 1 times 1 over x squared. To the nth power. Okay, so by the power of a product rule for exponents, you can kind of distribute that nth power to both of those factors. So that gives you the sum from n equals 0 to infinity of negative 1 to the nth power times 1 over x squared to the nth power. Or if you wanted to rewrite it, you can make the sum from n equals 0 to infinity of negative 1 to the nth power times x to the negative 2n, which would be your power series. All right, so any questions on that one? All right, I'll leave that up for a little bit. Right. Wrong one. Okay, so let's say, for example, that's getting ready to shut off. For absolute value of r is less than 1, the sum from n equals 1 to infinity of n to the r n minus 1 equals 1 plus 2r plus 3r squared, etc., 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 which equals 1 over 1 minus r squared. Sometimes they'll actually give you their own geometric series and want you to create a power series from that. Okay, so use this to find the power series. For f of x equals 1 over 1 minus square root of x squared. Okay, so for this one, our goal is to match that series. Okay, so if we know our f of x, oh, actually, I kind of skipped ahead there. No, actually, nope, I didn't. I can actually do it that way. So f of x equals 1 over 1 minus square root of x squared. The only difference between the two is the fact that just made r equals square root of x. A is already equal to 1, that matches. R equals square root of x. Kind of separate that a little bit. Okay, so that means your sum from n equals 1 to infinity, I'm about to put a, of n times r to the n minus 1